So good evening to all. Welcome to week 11 discussion for the electrical machines 2 course. So last week we were discussing the concepts of yeah, single phase induction machines. So as a part of that we were arriving at the equivalent circuit of single phase induction machines. How exactly the single phase induction motor works and what are all the torque equations involved. And for that we started with the discussion ideology of assuming an auxiliary winding along with the main winding, so arriving at this particular net torque equation. Now if you see, this is the total net torque when there are two phases involved. So but if we look at the original circuit, there were no two windings and all. So we will discuss few bits today towards the actual equivalent circuit of a single phase induction motor, and then we will continue with the current week topic. uh, uh, so that is synchronous machines. But before starting synchronous machines, let's just wrap the key discussions in the single phase induction motor, where we will arrive at the actual running conditions of the motor. So this particular slide which I am showing, which this we have arrived at in the last week's discussion, this net torque equation. So here we are seeing two different torques, that is forward torque and backward torque, and the total Vm input voltage, that is Vm1 plus Vm2. Now if we look at the original circuit, so let me just take some slides. Yeah. So if we look if you look at the original circuit and compare with the above circuit which we have just seen, so this is the original circuit. We have the rotor, and then we have a main winding. This is the input supply we are giving here, AC, which is Vm magnitude, and the current flowing through this winding is Im. You remember this discussion last week, right? Now this is the main circuit, original circuit, I can say. So everything is okay if you see the previous circuit, which is having an input Vm, whole Vm, and the current flowing is the Im by 2 here, half of the magnitude current. So only disturbing thing which we have observed is total voltage is matching, but the current is Im. But in our circuit, which we have arrived by assuming the auxiliary winding is Im by 2, which is half of it. So my circuit is taking only half of the main current which is supposed to flow. Now, if we somehow make this Im by 2 as Im, maybe if we can change this Im by 2 to Im, then everything will be same as my single phase induction motor. So I will write it. Original circuit, equivalent circuit. So original has the parameters of Vm and Im. Equivalent circuit is having Em and Im by 2. So what we will do is, if see how this is the total voltage divided by all impedances is giving rise to Im by 2 circuit. Im by 2 in the equivalent circuit. Now we want to change this Im by 2 to we have to double the current. Now since Vm here is same, and what only I can do changes are in the impedances. So now what I will do, I will divide all the impedances by half. by 2 to make the entire impedances as half. So Vm all impedances divided by 2. So this will be 2 will come at the top, Vm by all impedances. So what is this factor? Vm by impedances is Im by 2. So 2 times Im by 2. So you were arriving at the actual current which is supposed to flow. That is, Im should be the current drawn from the supply. So now it will be same as the original circuit. So yeah, let's make this similar change in our equivalent circuit also. So this is the equivalent circuit. Now what I will do, I will have all the impedances here. Divide every impedance by 2 and current automatically will go from Im by 2 to Im. So the first circuit, which is the forward, this one, we have a resistance here, reactance, magnetizing, and in the load side we have a reactance and a resistance. Okay, and now we are going to the second circuit. Again, a magnetizing, reactance, resistance. Now this is the total circuit, and here we are giving the supply, which is Vm bar. So the first circuit, R1 by 2, half all the impedances, X1 by 2. This is J Xm by 2, X2 dash by 2, R2 dash by 2s. This is the forward circuit, forward equivalent circuit. And now this is R1 by 2, by 2, and this is X2 dash by 2. This is again Jxm by 2, but this resistance is backwards slip, that is 2 minuses. Okay, you remember the last week discussion, right? So here again plus minus will be there, and here plus will be there. Total voltage is Vm, and automatically the current now would be Im, not Im by 2 anymore. So this is how so if you see the motor for it, our original circuit. So this Im, and here we have Vm here. This is the equivalent circuit for the original single phase induction motor. Now what we can do some modifications here. So we are trying to arrive at the torque equation for this. So what I will do, there are many series resistances and parallel impedances and all. So we will combine all resistances first and the impedances first. So one second. We will combine all the resistances and reactances so on to arrive at the final equivalent circuit. So now see what we will do. So initially there is R1 and X1. See this one, R1 and X1 by 2, and here we have another R1 by 2, X1 by 2 in series. So these two are in series, and this entire branch Xm and X2 by 2, R2 by 2, that's in parallel, right? And there is another series, and again Xm by 2, this another similar branch is in parallel. So we will just write in that fashion. So R1 by 2 and R1 by 2 will give the equivalent R1, X1 by 2, X1 by 2, X1, and there is a parallel branch. This is rotor side parameters in the forward circuit, and then we will have another branch, rotor side parameters for backward circuit. Forward field, backward field, there are two fields, right? For this, we are having the supply here. This is Vm. Now, if you see, the current will be Im here. So I'm writing the parameters R1, X1. So this is R2 dash by 2S, forward field load resistance, rotor resistance. And this is X2 dash by 2, and this is Xm by 2. So here again, R2 dash by 2 into 2 minus S, this is X2 dash by 2, and this is Xm by 2. So we saw the currents flowing through these two forward field, that is IF and IB. Are there in the original circuit? Yeah. So if you see this current IF1 and IB. Now these are IF1 and IB1 when the total current is Im by 2. So now since the Im by 2 has become Im, the input current is doubled. So the current flowing through this resistance and reactance will also be doubled. So IF and IB will now become 2IF and 2IB. So this, right? The reason also you must relate. Previously it is Im by 2. Now Im by 2 became Im. So IF and IB will become 2IF and 2IB. So this is the final equivalent circuit for our single phase induction motor. So let's calculate our torque and also air gap power in the circuit. So torque, if it's in synchronous watts, if you remember, it's nothing but the air gap power PAG only. Now let's calculate that. We have two torques here, forward torque and backward torque, and we have this formula here, this T net TF minus TB. So here we don't have two phases here, we have only one phase. So IF, like, it's not single phase air gap power, that is IF square multiplied by R2 dash by S, whatever IB multiplied by R2 dash by S. So if you see this torque equation here, uh, see, torque in synchronous watts is nothing but air gap power, because torque is equals to PAG by 2 pi ns, which is in synchronous speed. So torque in synchronous watts is nothing but air gap power. So I'm writing it here. I current square multiplied by R2 3 I2 square R2 dash by S is the air gap power. So here 3 is 3 phase, here it is single phase. So only one time we will multiply, and the resistance here is R2 dash by 2S multiplied by the current is 2IF square minus, in the backward field circuit, R2 dash by 2 into 2 minus S multiplied by 2 times IB square. So if you bring this outside, now we have 4 times R2 dash by 2S IF square minus 4 times R2 dash by 2 into 2 minus square IB square. So cancel 2 and 2 times, and 2 here 2 times. It will be 2 R2 dash by S IF square minus 2 R2 dash by 2 minus S IB square. So the one interesting thing which we can see is, compare this equation. Let's say this particular equation is, I will write it in separate. Torque is equals to 2 into R2 dash by IF square equation B, and we name this particular equation as equation A. Remember, Now compare this equation A and equation B. So this equation A is of two-phase machine net torque. I will just write the same here, 2if r2 dash and 2ib square r2 dash by s. Both are exactly same if you see. So this is equation A we got. So both are exactly same, but the properties are different. Because when we are arriving at the equation A, we assume there are two-phase machine, right? And now for B, it's only single-phase machine. Both are equal, but their properties are different. So what I'm trying to say is equation B is the torque of our new circuit. So the moment we divided all the parameters by 2, all the resistance and impedances were half, and the current became twice. So the power also became twice. So then no need to multiply two times because it's only single phase machine. So the circuit is now single phase induction machine equivalent circuit running on only single winding. That is main winding. There is no auxiliary. There is nothing. So we just did some modifications and the output we got is exactly related to a single phase machine. So that's what this equivalent circuit actually represents. There won't be any auxiliary but the way we have started our discussion with an auxiliary winding is because to arrive at this particular torque equation by assuming there is an auxiliary winding. But anyhow, we didn't give any supply to the auxiliary there. We just assumed there so that the torque will be developed and then we arrive to the torque equation. But then later we combine that into a very single phase machine where we have just doubled the current and half the impedances. So we arrived at the single phase equivalent induction motor circuit. So in general, how people will represent this torque equation is they will write this IF as I1 square R1 R2 dash by 2s minus I2 sorry, I square R2 dash by 2 minus s. So I1 is 2 times of IF.
So this is torque.
Yeah, this is torque or air gap power. Torque in synchronous watts and power in watts.
No, but torque it means like omega s will be there.
That's what I'm telling you. Torque is air gap power by 2 pi ns. Right. So this is synchronous speed. We discussed it. So what is this unit of this torque here? It is Newton meter, right? So if I am writing torque is equals to PAG, so this is the constant term which is having synchronous units. So I can write torque is equals to PAG if power is in synchronous. See, if I multiply my torque with 2 pi ns, it will be power air gap power only. If the unit of torque is synchronous watts, then it means it is same as air gap power. So we are eliminating this particular 2 pi ns and writing this unit as synchronous watts. If you want to write torque in terms of Newton meter, then you have to divide this entire thing by 2 pi ns. You understand? We have discussed this in our induction machine formulas. You can refer to that. The thing, it's not difficult. So it's PAG by 2 pi ns is torque in Newton meter. PAG is the torque in synchronous watts. So we are clubbing that 2 pi ns, eliminating that, and we are representing it in a synchronous watts unit. Even we have solved one problem, I guess. In this uh, problem, they will directly give the torque is 5 synchronous watts or something like that. Then it means that the torque is PAG by 2 pi ns included. Yeah. So this is what single phase induction motor equivalent circuit looks like. So this RF, if you see this particular equivalent circuit, there is a parallel branch here. If you can solve that a parallel branch, and you will get two resistances and reactances, RF, XF, and RB and XB, so that the equivalent circuit can be look like. So to solve this equivalent circuit, usually people simplify that parallel branches. So here there is a parallel branch, RF, XF. So another parallel branch here, RF and XF. It's VM, VM. So this is R1, X1. So we can write as RF and XF, RP and XP. Now we know that torque is equals to I1 square R2 dash by 2S minus I2 square R2 dash by 2 into 2 minus S, where I1, I2 we just wrote 2IF and 2IB, right? Now we can write the entire term. This term, this term into Im square Rf minus Im square Rb. So here Im, since this entire circuit is having the same current flowing, this resistive equivalent we can say. So equation 1, this is equation 1 and this is equation 2. Any equation you can use, but RF RB would be the series current. So if you replace this RF, and the current flowing through will be same as Im, right? Im will flow through RF and Im will also flow through RB. So we will replace this Im, RF, RB. So if you are writing in rotor resistances, it will be I1 and I2, that is IF and IB. If you are writing it in RF and RB, it will be same as magnetizing main supply current. Okay, now let's verify this circuit, whether it is satisfying our induction single phase induction machine concepts or not, because what we arrived at this last week. So induction single phase induction machine has two properties. One is there is no starting torque, and when you run the machine with some prime mover, then the slip exists and running torque will exist. So that we will verify it here. So again, I'm just quickly drawing the equivalent circuit in this parallel branches, so you can actually see this. This is R1 X1. So let's analyze the circuit at the starting. So at the starting, what is the slip? Slip will be 1, right? So wherever it is slip, we will replace it by 1. So this is R2 dash by 2S, it will be R2 dash by 2, and X2 dash by 2, this is XM by 2. So here it is R2 dash by 2 into 2 minus S. 2 minus S will be again 1. So it's again R2 dash by 2. So here X2 dash by 2, XM by 2. So this currents flowing here and here, and the total current is Im. So yeah, now see the torque equation and tell me the current flowing through it. Like what is the torque flowing through it? So this equation you have now I1 R2 dash by 2S and I2 R2 dash by 2S. Now I1 and I2 will be same or not? Because if you see R2 dash by 2, X2 dash by 2 and XM by 2, same parallel branch. Here also R2 dash by 2, X2 dash by 2 and XM by 2, same. So IF and IB will be equal to now I now, right? Both are same. Now the current will be I square, the resistance part is R2 dash by 2 minus same current I square. In the back forward and backward resistances are same in now at the starting, S is equals to 1. So this is 0, TE is equals to 0 at the starting. So this condition is verified, that the starting torque is absent for our induction machine in the single phase condition. So what is the another condition which we discussed last week? It is single phase induction machine will have a running torque. Running torque means it will have some slip. Slip is not equals to 1. Slip at running condition. Now if you see that particular condition, For other slips, slip is not equal to 1. That means it is in running condition. Now R2 dash by 2s, it's in the rotor circuit 1, and it is not equal to R2 dash by 2 into 2 minus s, right? So they both are not same. So the currents flowing will be not same, and torque will not be equals to 0, right? So your torque will exist. So during running condition, running torque will also exist. So again, as we discussed in previous week, uh, starting torque won't be there, and also running torque will be there. So that's how we have analyzed the single phase induction machine using the equivalent circuit. Now that's all related to single phase induction machines. So how the equivalent circuit of a single phase induction machine can be derived. So what are all the parameters involved, and how we arrived at this particular equation using auxiliary winding concepts. So that's all. That's how we close the discussions on the single phase induction motor, and now we will move on to the important topic of machines, that is synchronous machines. So see, synchronous machines is way easier to analyze compared to induction machines. But only thing is the concept should be very clear. So it's very simple concept of machines. This is synchronous. The synchronous machines. But let's start a discussion on synchronous machines. Okay. Now, as I said, it is easier to analyze. You just have to have your concepts clear in your mind. So, in case of three-phase induction motor, what we have seen is when we are energizing the stator, uh, anyhow, rotor is not requiring any supply there. So we are just energizing the stator. Rotor doesn't need any energy like supply, and it's getting energized by the rotating magnetic field and all. So that's why we are calling this three-phase induction machines as singly excited motor. So I'm writing it here. Why it is singly excited? You just have to excite the stator of this induction machine. So automatically your rotor will rotate. Now, whatever magnetizing current that is needed by the machine in the induction machines concepts, that is drawn from the supply only. So Xm, whatever it is the IM current. It is drawn from the supply and the motor will run. Now, one more condition what we have seen in the induction machine. So the total B net, the field which is present in the motor will be constant. From no load to full load, the B net will be constant. So if you remember the three-phase induction machine's voltage equation, per phase voltage is 4.445 F winding factor multiplied by turns, right? You remember this? Now, once we have fixed the supply voltage and also the supply frequency, the moment these two are getting fixed, so the rest are all constants only. So this flux is constant then. So flux per pole, flux per pole here is fixed, right? If flux per pole is fixed, then my B net is fixed, right? Now in synchronous machine it's different. Even though your voltage, supply voltage and also the supply frequency is fixed, the net air gap flux may change. If we do something else, we will be discussing that for what we will be doing. So if we do something else, this air gap flux will change. So that's how these two machines are different. And two key points which I will write now is synchronous machine is a not a singly excited machine. It's a doubly excited machine. So we can also operate this synchronous machine as both generator and motor. But the important point is synchronous machine is a doubly excited machine. Now, what exactly this doubly excited means? We have stator and also the rotor. Now on the stator we are having this three-phase distributed winding, right? Same as this induction, like any stator would have some slots will be there. We will be winding our three-phase distributed winding. But here the rotor, which coming to the cylindrical rotor or any kind of rotor we are having, you will you will have some slots also on the rotor teeth. Some slots and teeth will be there on the rotor. It just we will have the winding on the rotor also. But important thing is it's not a three-phase winding. It's just a wire wound on the rotor slots. That's it. I'm just trying to draw here. I'm drawing the stator teeth now. Let's say your stator is like this, and you are having a balanced three-phase winding in these uh, slots of this particular stator. Let's say here we have. So this is three-phase balanced winding, and this is stator. Now in this inside this we will have a rotor which is also having this teeth. So now see, I am just winding like I'm there are just slots here. I'm placing my winding and then I'm just see this is not just any three-phase winding. I'm just coil will be there. I will just take a wire and wound around these slots. So this is my rotor and it will just a normal winding. Now for this rotor, since it's a doubly excited machine, rotor we will give a DC excitation. So now this is whatever coil that is present on the rotor, we call it as a field coil. Okay. Now see, it's look like this. The stator is having a three-phase winding, and the rotor is having a DC excitation. DC current will flow. So now what we will do, once we excite the rotor with DC, the DC current will flow such that it will have some lines of force. Using your right hand thumb rule, if you see, so maybe this is your rotor. Let me just draw here. You have a stator here, three-phase winding, but on the rotor you have just some winding wound on it. So if it is dot here, assuming this is cross cross cross, using this right hand thumb rule, the flux lines would be like this, top, right? Now the lines of force according to thumb rule you will have like this. Now if your rotor is cylindrical, you will call this synchronous machine as a cylindrical rotor synchronous machine. So there are different types of rotors. Some rotors of the synchronous machine will also be in projected pole type. So like this. So this is a salient pole you call. So this is a two pole. Let's say you have, and here the winding is there, and this is dot dot dot. This is cross cross cross, and here also the flux lines will be like this. And this particular rotor is called a salient pole rotor. So you will call this synchronous machine as a salient pole synchronous machine. So based on the rotor structure, you will call the name of the synchronous machine. So now the stator winding is three-phase winding. In terms of synchronous machine, we call this as a armature, three-phase armature winding, and the winding on the DC machine is just a DC winding, field winding, as I said. So next thing which we will discuss in this synchronous machine is the ratings of this synchronous machine. So usually you observe this ratings of synchronous machines are very large compared to your induction machines. Now this single phase induction machine which we discussed today and the last week, their their power ratings are only in the order of watts, not more than that. Now coming to three-phase induction machines, these are a bit higher. You see in the industries and all, maybe few kilowatts, 100 kilowatts, 200 kilowatts, etc. But coming to synchronous machines, can anyone guess what's the rating of the synchronous machines usually they use in the industries? So they can go up to megawatts. Now, can anyone tell the reason behind this synchronous machines having the higher and higher this ratings? Because see the fact that induction machine has few drawbacks, like it draws the entire magnetizing current from the supply lines only, right? So the supply has to provide for that magnetizing current. Now this makes this motor to have very low power factor. Now since particularly during very light load condition, during no load of course your current will lag your voltage by 90 in induction. Now when there is very light load, it's around 80 degree or 70 degrees. Now at that condition your power factor cos of that angle will be very low power factor. So at light load you will have very poor power factor, and if it's a very large induction machine, so it has to draw that much large magnetizing current from the supply itself. So usually people don't go for this high rating three-phase induction machines. So but in case of this synchronous machines, if you see excitation is completely from a separate source. You are having a separate DC source, or you can even go for a battery bank, right? Now we know that if stator is carrying this balanced three-phase current, it will produce some RMF, so it will have some field Fs, right? Now stator field, that is RMF will be there, and it is rotating with the speed of Fs. That's good. Now if we are exciting the rotor with a DC, so what will happen? So will there be any rotating magnetic field? No. Since it's a DC rotor field, DC, so you will have some field, but it's stationary. It's not rotating, because when the current carrying conductor you're giving some DC excitation and it will have generate some field. That's okay, but it's stationary only. It won't be rotating like three-phase winding field. Now if you want to operate this machine as motor or any generator or something, you want to rotate this machine. So your motor has to rotate, your machine has to rotate. Now your stator is having this RMF, but your rotor is having this DC field. Will the machine rotate or not? So will this machine produce torque? Definitely it won't, because we know that for production of a steady electromagnetic torque, the relative speeds between stator field and rotor field must be zero. So what happened in the induction machine? Your rotor field and stator field both are rotating with the speed of Fs, so that the relative speed between rotor field and stator field is zero. Because a stationary observer, if he seeing the rotating machine, he should say that both the fields are moving at the same speed. Then only the angle between them will be constant, and then only they will produce a steady torque. But now, if you can see this synchronous machine, a stationary observer will say, okay, this DC rotor field is DC, stationary only. That there is no speed of this rotor field. But I can say that stator field is having a speed of Fs and it's rotating in with respect to time, right? So what we can conclude from this, if we want to run our synchronous machine as a motor, it got no starting torque, right? It has no starting torque. So that's what we are concluding it. Synchronous machine as motor, no starting torque. So now what to do? So if this machine has to work, what I should conclude that rotor must also rotate physically in the same direction as the stator field with the same speed, right? So you're having some stator here and rotor here, and you're rotating, let's say in anti-clockwise direction, Fs is the speed. Say rotor which is having the current IDC will have some field Fr. You have to somehow make this field rotate with the same speed as the stator field. So what I'm concluding, for any synchronous machine to work, rotor must run at speed ns, which is the speed of the stator rotating magnetic field. That's what I'm concluding. So whatever speed my stator is having ns, so my rotor will also have same ns, so that I will have the both speeds fields rotating in the same direction. So that's how we say this in the synchronous machine. Both rotor and stator have the same speed, synchronous speed. Now, what will be the power and torque for a synchronous motor operation? So to look into that, we will just have to go with a very simple phasor diagram of synchronous motor, and it will be very easy to derive the power and torque equations from that. So, as I said, it will be very easy to analyze compared to induction machines, but you just have to have the basic concepts very clear. So, we will first draw the phasor diagram, and we will try to find the torque expression from that. So, in case of synchronous motor operation, motor means what? It is taking use of supply. Supply is giving energy to the motor to rotate. Now, here is my motor, okay, and I'm exciting it using a supply. It will have some impedance, series impedance. I'm calling it as this ZS, and here I have the supply. I'm taking my supply as a reference. So from supply, energy is being sent to this motor. So as I said, this three-phase winding, IA, armature current, you can call it. It is drawing this power from the source because it's a motor. Now I'm calling this series impedance as ZS, and the motor will get excited, and I'm calling this excitation voltage as EF. Now the impedance is ZS, and my bus voltage, my supply is V at an angle 0, and since it's a motor, it will be drawing power from the source. So it will be from source to the motor. It is in the current direction will be in that from right to left. Now IA we assume in the direction, and this will be the EF. So let's assume that our motor is drawing a lagging power factor load. Assume it could also draw leading power factor load, anything, but I'm just assuming the case first. It is drawing a lagging power factor load. So my load is some mechanical load on the shaft, and it is drawing some lagging current. So current lagging means what? My supply voltage and the IA both are lagging behind. So the equation would be EF is equals to total voltage V minus this drop, right? V minus Ia into Zs. So Zs is, if it is Ra and Xs, that is synchronous reactance and the armature resistance. So I can write this as Va minus IaRa minus JIaXs. Usually this RA is very very small. Usually people neglect this resistance of the synchronous machine. But anyhow, this is the equation of the excitation voltage. Now let's draw the simple phasor diagram. I am taking my reference as V. As I said, V is at an angle of 0. And now V and Ia are lagging power factor load. Just writing here, lagging power factor load. So V and Ia would be lagging. This would be my Ia. So this particular theta, what I'm calling is a power factor angle between voltage and current. Okay. Now, what is the equation? V, you have to subtract Ia Ra drop and again subtract the Ia excess drop to get the excitation voltage. Now, Ia and the Ia Ra drop will be the same phase because resistance has no phase difference. So, if I am having this Ia and I am assuming this as a Ia Ra drop, and I have to subtract this Ia Ra drop from V. So, V is here and minus Ia Ra, I am writing it in this direction. Okay, and then we have this Ia excess will be at 90 degree J, right? Axis will have exactly 90 degree from the Ia phase. So if it is I and this is Ia excess, so again we have to subtract this from this V to get the E. So V minus Ia Ra and minus Ia excess. This is this one. This is okay. This will be exactly something like this. It's perpendicular to here. Anyhow, so it will be minus Ixs. So you see this V minus IaRa minus Ixs will be my EF, that is the excitation voltage, which will have the motor developed excitation. So the angle between V and Ia would be your power factor angle, and your angle between V and EF will be delta. You represent delta with the load angle. Usually it's the voltage angle between the voltages. So therefore, if a motor is drawing a lagging current, now we see the length of EF, the this particular excitation voltage, that is a field that is developed in the rotor EF, and the resultant total field, that is V here. The length of EF and V are different, and the excitation voltage length is very less compared to V. So that I'm just writing it here. Excitation EMF, that is EF, rotor field, and the resultant field from the supply itself, that is total field. So here if you see for a lagging power factor load, the length of EF is less than your input voltage, right? That's what we saw in the phasor now. So your resultant is more than the excitation. So it's not well excited to have a resultant field same excitation. So you call this condition as under excited. So if your synchronous motor drawing a lagging power factor will operate in the under excited condition. Now it's simple to relate from the phasor diagram. Now if you see the complex power drawn by this particular motor, you know the formula for it. I see, I'm just So complex power drawn by the motor, let's calculate the complex power delivered by the source first. How much is my source delivering? From there we will see how much your motor is drawing. Now I'm just drawing the, let me check a fresh sheet. So this is your excitation, and then you will have your series impedance. Here we have the voltage V is at a certain angle of beta. Beta I'm taking it as an impedance angle, and here EF I'm giving it an angle of minus delta. Why it is minus? Because EF always below voltage, right? So for motor condition, whether it's lagging or leading, your EF will always below, or like if it is V here, you will have EF always below. So it is zero, it is delta. So EF is always at an angle of minus delta from V. Okay, that's the reason why it is minus. So what is the complex power delivered by the source? VIA star. So here IA, if you see, what is the current? Now current is in this IA. V minus this voltage difference divided by the impedance. That's how we can calculate it. V at an angle 0 minus EF at an angle minus delta divided by ZS at an angle beta. So this is IA. I'm just dividing it into fractions. V by ZS minus beta minus EF by ZS minus beta minus delta. Now this is IA. What would be the IA star? It just be negation of this all these angles. V by ZS at an angle beta, negate opposite of the angle, minus EF by ZS delta plus beta. Take the minus common and eliminate it. Now if you calculate the S is nothing but V multiplied by this IA star. So multiply V for the entire expression. You will get V square by ZS at an angle beta minus V into EF by ZS at an angle delta plus beta, right? So now this is the complex power delivered by the source. So if you see the real power in this, in the total complex power, what is the real power? So S is nothing but P plus JQ. Now I can write these angles in terms of cos theta plus J sin theta. So all the cos terms would come under real power, and all the sin terms would go for reactive power. So I'm just writing the real power P V square by ZS cos beta V into EF by ZS cos delta plus beta. So yeah, so if you neglect, you can further modify it. Actually, this beta is but the resistance and the reactances. So here, if you neglect this ZS is RA plus JXS, right? So usually the resistance will be very small magnitudes. If you neglect it, your ZS will be nothing but JXS, nothing but XS at an angle of 90, right? J is 90 degree. Now your ZS at an angle of beta will be XS at an angle of 90. So you replace ZS by XS and beta by 90 in here. So you will get V squared by XS cos 90 minus V into EF by XS cos 90 plus delta. So anyhow this will be 0 cos 90, and cos 90 plus delta will be minus cos delta. So minus minus will get cancelled and it will have positive. So the real power you will get is V into EF by excess sine delta, cos 90 plus delta is minus sine delta, right? Now this is the real power what we have got in the motor operation. Now let's compare it with the generator mode. But before going to generator mode, let's see the leading power factor condition also. It's simple. Like let's have a comprehensive comparison here. Now this side I'm having the motor discussion, and also let's do it for the generator here. Very simple discussions. So motor I will have, sorry, okay, no, that not a problem. EF here and XS. I'm neglecting the resistance part. So JXS and motor current is drawn by the motor here. Now equation remains same whether it's a leading or lagging. For the motor it's always V minus JIAXS, right? So first lagging we already saw. I'm just writing it. So if it is V and it is IA and V minus IAXS, right? There is no RA now. RA is neglected. So this is EF. So this is theta and this is delta and this is the minus like IA axis drop. Right now, if you see for the leading power factor, so this is V and your current is leading right here. This is theta and V is here and IA axis will be like this and it will be minus IA axis. This will be like this, minus IA axis. V minus IA axis. The resultant would be EF. Now you see the length of EF here. So in the lagging condition, what we have found out, the length of EF, that is the excitation voltage, is less than the resultant V. Now here the excitation voltage is more. So the length EF is greater than V. So it is over excited. So here is EF less than V under excited condition. Now similarly, if you look into the generator condition, generator will have this EF and JXS and this is the bus, some grid. Now generator means it will be supplying to the grid, right? It is JXS, the direction is IA here and now the equation will change. So for the generator EF is equals to V plus JIAXS, right? Now if you see this V plus JIXS and let's look at the lagging power factor. You have the reference V and you have a lagging power factor. Now IA would be like this, the power factor angle, and you have to add the IA excess drop. So this will be the IA excess here and we will have the IA excess here plus IA excess and V plus IA excess will be EF. And let's draw for the leading power factor also. And for the leading power factor, if you have this V like this and you have your IA leading power factor angle and IA axis like this, right here. Now this is the IA axis. V plus IA axis will be here, EF. And the both, this is the delta and this is the delta. Now the length, if you compare, the length EF is greater than V here. So that will be the over excited condition. And here if you see EF length is less than V, that is under excited condition. So as far as your gate concepts are concerned, so this particular slide which you are seeing here is very important. If you understand this concept, at least one problem will definitely be there in your gate exam. So here we have 4 different conditions inside this synchronous machine. That is synchronous motor operation, synchronous generator operation, and within the motor and within the generator we have lagging and leading conditions. So how exactly this um phasor diagrams would look like, and which condition we will say as under-excited and over-excited, and these are very simple and important discussions in the synchronous machine. So I would request everyone to go through this concepts on synchronous machine. These are very easy and very important for gate also, and you will definitely get one to two problems in this synchronous machine concepts. This there is another topic also, V curves and inverted V curves. So that concepts in this phasor diagram concepts. So you will definitely get the problem from this, and so it's very easy also. So I would request everyone to go through concepts of synchronous machines and revise them thoroughly, understand the concepts, and it will be very easy to solve the problems. So with this background, let's just solve the problems, few problems on the synchronous machine. Please take pen and paper with you and solve with me. If you understand the problems which we discussed right now, and it will be not very difficult, but it's a tricky, I would say. You have to relate the conditions whatever given in the question to the formulas and concepts you know. Thoroughly read the question and note down the data they given to you, and what exactly they are asking at what condition. So that's the important thing in the synchronous machine concepts. So let's see this problem. So we have a three-phase 440 volt line to line delta connected synchronous motor. Okay, so this motor is having a synchronous impedance of 1 plus j5 ohm per phase. So this is what ZS is. So I'm writing down the data here. Three phase 444 line to line voltage, and ZS is 1 plus J5 ohm per phase, and we have an excitation voltage of 550 volts. So EF 550 volts line to line, and the rotational losses is 1 kilowatt constant. Okay, apart from copper losses, we have this constant rotational losses. So they were constant all throughout the operation from no load to full load. So it was given as 1 kilowatt. Fine. Now what we have to estimate? So we have to estimate the line current under the maximum power input condition. See, we were asked to estimate only the line current, whatever is the line current flowing through the machine. Under what condition? Under the maximum power input condition. So input power should be maximum. So what was asked? I line at P input maximum. So this is what asked. So for that, what we need first? First we need to calculate the input power, and then we have to maximize that input power, and then at that condition what is the current. Okay, so to get the input power first, real power, let's get the apparent power first. So once we get the apparent power, we can easily calculate the real power from the cost terms. So to get the apparent power, the formula is three phase 3 vi star. So v anyhow we know, I star we don't know, right? So how to get s, we need to have a calculation of I star. So to get I star, first we have to calculate the I. Now for a this given condition of motor condition, what is the formula for this particular I we calculated now? V minus E at an angle of minus delta divided by Z at an angle of theta. Theta and beta both are power factor angles only. So now you see, this is what we have to calculate first. Once we calculate this, we will put this I in the S, and once from the S we will calculate input power, and then we will maximize it, and then we will get some condition at that maximized condition, and then we will calculate the current. Okay, now let's calculate this I. So I have, so I star would be V by Z an angle of theta, I star, this is the conjugate of it, now minus E by Z minus delta minus theta. So it will be delta plus theta I star. Now I got I star. So now I will calculate apparent power 3 V I star. So my apparent power would be 3 multiplied by V. So 3 V squared by Z at an angle theta minus V, okay, V E by Z at an angle delta plus theta whole multiplied by 3. Now from this what will be the real power? 3 V squared by Z cos theta minus VE by Z cos delta plus theta. Okay, fine. So now I calculated the input power. So this is the input power. Now this should be the maximum. So I have to maximize this particular input power. There is a long process to find the maximum. So we can calculate the derivative equal to 0 and maximize it, the values and all. But by simple observation also you can tell this. See, here the theta, so z is given 1 plus 5j. So it will have some z at an angle of theta, which is tan inverse of 5 by 1, which is theta is already fixed. So in order to maximize this, theta is already fixed. Now this delta plus theta, this term could be variable. Now see, this is an entire expression. To have this power maximum, this entire term would be minimum because this is your subtracting from this particular term. So this term should be minimum means cos delta plus theta should be minimum. So P max implies that cos delta plus theta should be minimum. So what is the minimum value of cos? It is minus 1. So in order to have this minus 1, so your delta plus theta should be how much? 180. So that's the condition to have your maximum power input condition. So if I can manage delta plus theta is equals to 180, then I can guarantee that my input power would be maximum. So that gives my maximum power condition is equals to 3 V square by Z cos theta. So this will be minus 1 and minus of minus plus VE by Z. So this is the maximum input power expression. This is what we got from the inference, the condition they have given. Now at this condition, we have to calculate the line current. So line current means first we will calculate the phase current, which is V minus E delta by Z theta. And then we will multiply it by root 3 because it's a delta connected rotor. You will get the line current. Now let's see whatever data we have given, whatever data we were given to it, and we will substitute here to get the power and also the current. Now okay, so my P whatever data I'm writing it here. V at an angle is given, it is 440 at an angle 0, and E at an angle minus delta. So it was given 550, but delta we don't know. And theta is nothing but z we have given. Z is nothing but root of 1 square plus 5 square, root 26. It will be around 5.09 something ohms. Now theta will be tan inverse of 5 by 1. So it is around 78.69 degree. This is the given data. Now the expression we have got for P max is 3 V square by Z cos theta plus VE by Z. So let's calculate it. 3 times 440 square divided by z, 5.09, multiplied by cos theta. Theta is how much? 78.69, plus VE 440 multiplied by 550 divided by z. Z is again 5.09. So can someone calculate it for me? I will also calculate. 440 square divided by 5.099 multiplied by cos 78 point multiplied by 440 multiplied by 440 divided by 7.4k plus 440 divided by 164. Yeah, that's correct. So again 440 multiplied by 550 divided by 5.099. So do this plus this one multiplied by 3 times. Yes, yeah, 164.7 kilo. How much you were saying? Yeah, that's right, Dinesh. So 164.7 kilowatt. So this is the maximum input power condition. Now let's calculate the phase current first. V minus E at an angle minus delta divided by Z at an angle theta. So this at the this maximum power condition, what is the condition we have got? Theta plus delta should be equal to 180 degree. Now delta would be 180 minus theta. So you substitute that delta here to get the equation. So V would be 440 at an angle 0 minus 550 at an angle theta minus minus delta, right? This is minus delta. Minus delta would be theta minus 180 divided by z at an angle theta. Yeah, z you can 5.099 at an angle theta. Theta would be 78.69. Can someone tell me the answer for phase current? Okay, directly give me the line current itself. Line current would be root 3 times of this phase current. How many amps? Substitute theta minus 180, like theta is 78.69. I request everyone to solve the problem. Okay, so you have calculated, Dinesh. So the answer you will get would be 261.1 amp. You please verify with your calculation also. This is the line current you would get for this first problem. See, the given condition was to estimate this line current in amperes under the maximum power input condition. Now, the maximum power input condition which we have to figure out first, because at that condition only you will get some relation between delta and theta, which would be useful for you to solving this line current expression. So because in this line current expression there is a delta, factor, which delta you have no information about. So the delta relation between theta and delta would be available from this maximum input power condition, right? So let's move to second question. So second question is estimate the power factor under maximum power input condition. So yeah, we have already got the power expression, power factor. Now we just have to calculate the power factor under this condition. So what is the power factor? It is now you have to calculate this power factor under this condition. Directly going with the input ZS will not be correct, because at this in maximum power condition, what is the power factor? That's important. You can't calculate directly with the Z and angle theta, current, that is angle between voltage and current, because at this maximum power input, you know already how much your maximum power is. So you know this particular power and you know VL and IL at this condition, then you will get the power factor here. So this power factor would be P max divided by root 3 times VL IL. So how much is the maximum power? We got 164.7 kilowatt divided by root 3 into 440 multiplied by 261.1. So calculate it for me.
Yes, sir, it is correct, the current.
Okay, okay,
But my question is, sir, with the current I am got an angle minus 34.
okay.
So cos of that is not a power factor?
Oh, that current has a value, right? Yeah, that current also you can calculate. How much is that cost? Can you tell me?
34.126.
What is the cost of it? 34.126. Yeah, that is also power factor. So because that current you got at the maximum power, either that way also you can calculate, either this way also you can calculate. So see, if that is correct, that is 34 point something, you should also get the same value here. You can verify it. Yeah, 0.82. This is 0.82 from what? Cost 34.
Yes, yes, sir.
Okay, now you can also calculate this one. I think this should also get the same thing. Let's calculate 164.7 divided by root 3. Yeah, 0.827 I got. Yeah. So this is the power factor under the maximum power input condition. You can also calculate from the phase or line current. Now let's estimate the net shaft power under the maximum power input condition. So since once only you have to get the relation for this maximum power input. At that condition, you can calculate all power factor, shaft power, line current, etc. Okay, anyhow, here we are asked the shaft power. So it is nothing but the output power that is at the shaft end, which is useful power, that is nameplate detail power, output power. Now to calculate the shaft power, you know the input maximum. So the maximum power input you know, and if you can subtract the losses from the maximum input, that's it, you got the shaft power. So output power is nothing but input minus losses. So input, which is maximum, minus P losses. So what are all the losses you have? You have copper losses and the rotational losses. So copper losses you need to calculate. Rotational is already given. So how do you calculate the losses? So input first we will write, it is 164.7 kilowatt minus copper losses would be three phase one, 3 times your phase current. Phase current is what? Line current by root 3, 261.1 divided by root 3 whole square. Resistance, how much is the resistance? It is 1 plus J5, right? It is 1 minus rotational losses, it is 1 kilowatt, which were given in the question, constant rotational losses. So if you do this, calculation you would get the shaft power. Please calculate that. 61 square plus 1 minus 164 700. I got 95.525 kilowatt. I hope you got the same. 95525 watt. It is 95.52 kilowatt. So this is the net shaft power in kilowatt under the maximum power input condition. Okay, now next question. Estimate the efficiency under the maximum power input condition. Okay, now we already got the output power and also the input power. It's nothing but just the division of output by input. Efficiency is P output by P input. Output is 95.5 kilowatt. Input is 164.7 kilowatt. So how much is this? 57.98. What is the reason for this very low efficiency? Can you tell? Can anyone tell me? What could be the reason? The reason is in the given synchronous impedances, the resistance value it is 1 ohm. So 1 ohm resistance is very high. It's usually that's not that much high, too high for the machine. Usually we neglect the resistance of because it's in the order of milliohms. But here we were given a 1 ohm resistance that is contributing to a lot of copper losses, and then it is reducing the power output power like anything. So that's why your efficiency is very low. But usually your resistance is not that high to get a very low efficiency. Okay. Now the same question, we have to estimate the line current under the maximum power output condition. Now how can we do that? So now we are shifting to the output side uh, calculations. So this is the motor. Now whenever you are supplying to your motor, the current is being drawn from the supply and the excitation voltage will be there at the output, the motor side. Now let's calculate the power at this condition. So the same concept which we have done in the previous power input condition. So I'm just drawing the circuit here. Now you can take any reference. Since we are asking the output condition, let's take your EF at reference and V at an angle delta. Anything could be anything. When you are solving, anything will give the same answer. But just for simplification purpose, I am taking EF at an angle 0 and V would always be at an angle delta because EF would always be below V for this motor condition. So V at an angle delta and EF at an angle 0, and this is ZS, and this is the output and this is the input condition. So EF, let's take E as reference here, and now equation would be EF is equals to V minus IAZS, that we know, and now we have to calculate the complex gross output power. So complex power S, same thing, first we will calculate the complex power, then we will get the real power from that. 3 EI slash at the output side, right? This is the output side. Now 3 EI slash I conjugate. So we need to calculate the current first. So current is in this direction. So I would be V at an angle delta minus EF divided by certain angle theta. Now IA star would be V by Z at an angle theta minus delta, the conjugate of it, minus EF by Z at an angle theta. Now S would be 3 times EI star. Now 3 would be outside. I multiply the whole expression with E. VE by Z at an angle theta minus delta minus EF square divided by Z cos theta. Now let's get the real power from this. 3 VE by Z cos theta minus delta minus EF square by Z cos theta. Okay, now can you tell me what is the condition for this power to be maximum? This is the output power and this should be maximum. So here what is the condition? Can someone tell me?
Theta equal to delta, sir.
Right, that's correct. Because you can't do anything with this term because cos theta is already fixed. The impedance term theta is already fixed. Z is equals to 1 plus phi j and is fixed. So you can't change anything. So you have to concentrate on this. So this particular term should be maximum. So this cos term should be maximum. Cos theta minus delta should be maximum. So what is the maximum value of cos? That is 1, and 1 would happen when theta minus delta is equals to 0 degree. Now theta minus delta is equals to 0, so that means theta is equals to delta. So if you can manage your power factor angle same as the load angle, then I can guarantee that my output power of this motor would be in its maximum state. So now let's calculate how much is this maximum output power. I will substitute theta minus delta will be maximum, and the cos theta minus delta will be 1. Now 3 times VE by Z minus EF square by Z cos theta. So calculate it. 3 times V multiplied by 550 divided by 5.099 minus 550 square 099 cos theta, same thing, cos 78.69. So yeah, tell me how much is this maximum output power. Please calculate with me. What 15 to any answer? So I'm writing it here. 106.5 kilowatt. So please verify you got the same or not. Okay. Now what we have to calculate? We have to calculate the line current here. So it's the same thing. Now you will calculate the phase current first, and then you will calculate the line current from there. So phase current is V at an angle delta minus E divided by certain angle theta. So 440 at an angle delta. So delta should be equal to theta. That condition is useful here to write this. Delta would be equal to theta minus 550 divided by Z at an angle of theta. 0.099 at an angle 78.69. So if you solve this current, you will get the phase. So now I line would be root 3 times of I phase. Yeah. So how much can you tell me? Get around 215.2 amps. Please verify again from your end. Okay. Now the same thing, we have to calculate the power factor under the maximum power output condition. So under the maximum power output condition, if you want to calculate the power factor, same thing you can go for the input power divided by the root 3 VLIL, but we have not calculated the input power yet. So we have calculated the output power, which we got 106.5. So let's calculate the input power here itself. So input power would be output power maximum plus losses, right? So this is 106.5 kilowatt plus losses would be 3 times your current square multiplied by R, that is your phase current plus your 1 kilowatt. Now we can calculate that 3 times phase current, that is 215.2 divided by root 3 whole square multiplied by 1 plus 1 kilowatt, that is rotational. So you solve this one, you will get the total input power as 153.8 kilowatt. Okay. Now you got the total input power. Now I can easily calculate the power factor. Power factor is equals to P input at output max divided by root 3 VL IL. So the input power is 153.8 kilowatt, root 3 into 440 into 215.2. So calculate this. 153.8 divided by 0.9378. So this is the power factor. Now we are asking to estimate the net shaft power under the maximum power output. So I think we already calculated this shaft output power. So your net shaft output power is nothing but the output power 106.5. So your net shaft output power is nothing but the output maximum, which is 106.5 kilowatt. Now next question is estimate the efficiency, same thing under the
Sir,
maximum,
what about this rotational losses?
where I added it here in the input side.
No, in the output power is which you have calculated.
Where you are saying this shaft power.
Yeah, in the soft power.
Shaft power is already eliminating this losses, right? Shaft power is actual useful
No,
power.
we have calculated output power. So this is after minus this rotational losses.
No, no. See, you have input. You will eliminate all the copper losses, and then you will have some power net power also, and you will eliminate all the rotational losses. Then you will have the shaft power. The output we have calculated, which here,
106.
yeah, 106. This is output at the shaft end. Input minus copper losses will give you net power. Net power minus rotational losses will give you output power, that is shaft power. You can refer to that power flow diagram which we discussed in the input induction machine side, induction machines concept. The same thing. Power flow will always be same. There will be input power minus stator losses, copper losses, rotor copper losses, and core losses, and rotational friction, windage losses, everything. When you will get the shaft output power. Here, output power is nothing but the shaft power. So when you buy a motor, there will be a nameplate details. That is the output power. That is the shaft power only. Not so confusing. You have to remember that your shaft power is output power. That is a useful power because the shaft power is what you directly connect your load to. Whatever power it is available at the shaft end, it can be directly useful, directly utilized completely by your load. Okay. Now efficiency under maximum power. Efficiency is power output at the maximum condition, maximum divided by input. So output power is 106.5 kilowatt divided by the input 153.8 kilowatt. 106.5 by 1. 69%, 69.24. Again, very less percentage of efficiency. Again, because of that higher resistance value. It's very impractical. So practically, you will have very less resistances. So yeah, that's it. I think this is the last point of discussion for today. Okay, so let's have a quick summary. Okay, before that, if you have any doubts in this today's discussion of synchronous machines and also the equivalent circuit of single phase induction motor, you can ask.
Here also, sir, power factor we can calculate the cos of the lagging angle of the
Right,
angle.
you can. Okay, so if you have no doubts, I'll just give you a quick summary of today's discussion. So that we started the discussion with the last week's continuation topic of single phase induction machines. So last week we have discussed how we can arrive at the equivalent circuit of induction machine by assuming an auxiliary winding along with the main winding. But we have not completed the discussion. We have derived at this point only the torque equation which you are seeing it. So it's the two phase torque equation having two fields, forward field and backward field. We arrived at this using the sequence components derivations. So but this week we have completed the discussion like how exactly a single phase induction machine equivalent circuit would look like, having zero starting torque and having non-zero running torque. So this would actually close the discussion of the last week. So then we have double the current by halving the impedances and then arriving at the final equivalent circuit, which is this. And then we derive the torque equation for that. Both torque equations remain same because our assumption is based on that such way both torques should be same. So that's what assumption means. So but physical significance of assumption also we have discussed. So what happens in assumption based torque equation, but what actual torque equation signifies. So that's how we arrived at this. This is the final equation, and we verify the two conditions. Starting torque should be zero, and running torque should not be zero. And then we closed the single phase induction machine discussion, and we proceeded for the synchronous machines, which is very easy machines in the rest of the machines, but it will need some basic concepts to be remembered. And now we started with the basic differences between induction machine and the synchronous machine. It's a synchronous machine being doubly excited, having a DC winding on the rotor excited by a DC source. That way we are generating two fields, one is stationary, one is rotating. So there is a need to rotate the rotor field as well in order to get a rotation movement in the machine. So we excited the machine and we rotated it, and then we saw how the fields are coming. Both stator field and rotor field have the same rotating field NS, FS, and then we saw some basic equations through phasor diagrams. How does a synchronous motor and how does a synchronous generator works, and their voltage equations and their phasor diagrams. And we did a good derivations on the complex power of the motor and the lagging condition. And the same derivations goes for all the motor and generator, leading and lagging. You can just recreate it. I just discussed for one condition. And then we had a good comparison of motor and generator based phasor diagrams for the four conditions: clubbing, motor and generator. How does a lagging and leading um, loads and their corresponding phasor diagrams look like. So with that discussion, we proceeded to solve some interesting problems. So problems were being attached with a given that condition. So at that condition only we have to solve for that. We got some relation between the angles delta and theta, because theta is fixed, only delta can be varied. So how the delta should be in order to have the maximum power, how the delta should be in order to have the maximum input power. So that way we have solved the equations problems, and then we have some good um, problems numerical solved. And basically we have two conditions: maximum input power and maximum output power. So those two conditions, we have got two conditions. First one is delta plus theta is equals to 180 and delta is equals to theta. So with those two conditions we calculate the line current, power factor, efficiency, shaft power, and everything. So that's how we close this discussion. So yeah, um, thank you for patiently attending the session and discussing, interacting with me, and solving the problems with me. It's good. So if you have any questions, or if you have any found any doubts or something during the week, you can raise the questions in the discussion forum. We will try to get back to you as soon as possible. And hopefully there is another extra 1 hour session during this Saturday. You will get the email from the team as an extra 1 hour discussion session where we can solve some overall problems on all the concepts from the week one. So this is the 11th week. There's only one more week left next week. So this weekend we will solve the overall problems from starting from week one. We will pick at least 20 to 25 problems and we will solve them. We will see how different concepts can be solved in this. And yeah, then we will meet for one last week next week, same time, Tuesday, for the last session on the machines. So that will end our electrical machines to NPTEL course. So again, thank you once again. Thank you all for attending the session and participating in the discussion. Thank you.